So let's continue with a couple of more definitions to help us describe motion. We will call these the fundamental of kinematics. For this class, we'll be dealing with rigid bodies. Now, a rigid body is an object that will not twist or deform during motion. So we can say that any 2 points separated by a distance d on that object will maintain that distance regardless of ensuing motion. So it will not get smaller, it will not get larger, it will not twist or skew, it'll remain the same. And your book has a weird blob-shaped thing to describe this. I'm going to draw a hammer just so it's something that's easier to keep consistency through. So if we were to take a hammer and just chuck it, the distance between 2 points on the hammer would stay the same regardless of how hard we chucked it for the most part. And when we want to describe motion, we can use two terms. So one would be translation. And pure translation is going to be that we move the hammer without changing its orientation at all. So if we imagine moving it in 2D space, this is true for 3D as well, but we'd keep the same orientation. So I can draw a hammer at one point, move it around a little bit, and draw it in the same orientation later on. And the mathematical definition says that any 2 points on the rigid body, they'll remain parallel during motion. And I just want to say that the line that they travel doesn't necessarily have to be a straight line, but if we were to draw 2 points on the hammer, those 2 points would remain parallel with the points underneath. So if we looked at the middle of the head or the bottom of the hilt, they'd remain parallel as they move, if you were to draw vectors of their motion. Now, if we had pure rotation, that's going to be an object where all of those points on a body are going to rotate about a single point. And the point can be somewhere on the body, it can be somewhere off the body. And the point at which they rotate, whether or not it's on the rigid body, is going to be called the center of rotation. And the reason we care about pure translation and pure rotation is that's all we need to describe motion. Because Chasel's theorem tells us that any motion of a rigid body can be described as having a rotation and a translation. And the order in which we describe it as rotation or translation doesn't matter. So let's say that you take a hammer and you're going to throw it and it spins a couple times before moving where its center is. That can be described as a rotation and translation. And now I slightly regret choosing a hammer as my object because that brings to mind a game called Stump. But if you take a device and you say, well, first we can say that to get from that starting point to that end point, that we can say that it translates and then rotates, or we can say it rotates and then translates. And the order of the rotation, if we're describing the end point, we don't care if it's rotating first versus translating first, because you're adding up two actions. So we're going to describe motion as having a translation component and a rotation component in order to understand how they move and in order to discuss how they move. So that's the reason why, is because we can think about how much an object turns and then how much their center moves in translation.